Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 6.1.2, which is Pythagorean Triples. Pretty straightforward chapter. We're just going to kind of start seeing if there's any patterns in these Pythagorean theorems. Now, in the past, I have asked you to kind of keep some Pythagorean triples in your back pocket, and we'll probably list them out at the end of this lesson. But before we get started with this problem here, 6.1.12 here, let's go ahead and review the special right triangle properties that we learned in the last episode, which is, first off, leading in with this 45-45-90 right triangle, otherwise known as the isosceles right triangle. Of course, the two sides being identical means that the two angles are identical, meaning they both have to be 45 degrees, because the 90 degrees is already being occupied by the right angle here. The pattern that we saw emerge from this was that both sides were going to be the same value. They're going to be x, and whatever the hypotenuse was going to be the legs side length times rad 2. And then the other one that we saw was a special right triangle with angles, let's see, 30 down here, and 60 up here. And it doesn't really matter where I put the 30 or the 60, it just matters that they're there. So across from the 30, we called that the shortest side. And of course, the drawing doesn't look like it's drawn to scale, but I guess we'll have to kind of deal with it for now. Across from the 30 is the shortest side. I called it x. Across from the 60 was the medium side. I called that x times rad 3. And then across from the 90-degree angle was the hypotenuse, and we called that double of the original x. And basically what these relationships allowed us to establish was that in these special right triangles, you don't have to be given all the information to find the third side, or even to find two other sides. Sometimes they might just give you one piece of information you have to find, and you have to find the other sides based on your knowledge of these special right triangles. So that's going to be the first part of today's lesson, and then we'll move on to a little bit more. So it says use the tools you've developed this far to determine the lengths of the sides of the triangles and blah, blah, blah. Okay, so first one here. Part A, 30, 60, 90 right triangle. So we have a length of 12 here. I'm going to go and fill in this 30 here. I'm going to move backwards. So since I've been given the hypotenuse, I'll go opposite the 30, which is going to be half of 12, which is 6, and then 6 rad 3. These should move ultimately pretty fast. This is a 3 rad 2 here. This one here, C, is not a special right triangle, but it is a Pythagorean triple. And in the past, I've had you write down PT 3, 4, 5, but because we have officially learned our Pythagorean triples after this lesson, we won't need to establish that relationship anymore. We can just kind of put down a 5, and that can now become assumed knowledge. With D, one thing to note about Pythagorean triples is that any of their similar variants will also hold the same pattern. And so notice how C and D are very similar, except the scale factor is 2. So with C being a 3, 4, 5, that automatically makes D a 6, 8, 10 special right triangle. And then from here, opposite the 30 degrees is 4, which means the hypotenuse has to be 8 because we're dealing with a special right triangle here, 30, 60, 90. I'm going to switch colors because I'm going to be writing on the black background here. So this is, looks like it's going to be 4 times the square root of 3. So again, should be moving pretty fast here with all of these special right triangles and Pythagorean triple relationships. 5, 12, 13 is another Pythagorean triple. Again, this is just an exercise in reflexes. We're just going to see how fast you can react. So now from here, if I go ahead and look at the scale factor here as 1,000, right? 3,000, 4,000, this has got to be 5,000 right here. And again, with this one, with H, it looks kind of threatening, but if you look at the scale factor compared to F, it looks like we're just dividing everything by 3 if we wanted to get from H to F. So it looks like you'd get 36 here because that is 12 times 3, 15, which is 5 times 3. So I just have to take 13 times 3, which I believe is 39. And I believe that's going to be the side length of H. And then 9, 40, 41 should be another Pythagorean triple you should kind of keep in your back pocket. Again, moving pretty fast here, so nothing really too crazy. I'll be back with the next problem. So we got Carl here asking a question about Pythagorean triples, and it says groups of numbers like 3, 4, 5, 5, 12, 13 are called Pythagorean triples. Why do you think they're called that? You're supposed to discuss this within your group, but basically they're called Pythagorean triples because that combination of numbers form a right triangle, and they're all whole numbers. Like, notice how we don't have any square roots that are lingering in the background. And so it's pretty interesting, these Pythagorean triples. We've talked about them at length as the year has gone through, and now we kind of have them officially down. What other sets of numbers are also Pythagorean triples, and how many different sets can we find? Honestly, we could go on and on. I could take the rest of the lesson to label out every single Pythagorean triple. The truth is, I don't know all of them, but the most common ones are 3, 4, 3, 4, 5. 5, 12, 13 is another common one. 7, 24, 25 is a common one that shows up a lot on different kinds of problems. 8, 15, 17, 9, 40, and 41 shows up often. And these are the ones that I really kind of keep in the back of my head because these show up most often. And then any similar variants. So I'll just go and write it down. I guess 6, 8, 10. Notice how that's a spawn of 3, 4, 5. It's just a scale factor of 2. So that would be an example of a Pythagorean triple that was similar. So I'll be back with the next problem. So it looks like Diana's having some problems that she's having with these questions here. And so let's go and see if we can figure out a pattern. And we're going to solve for each of the missing side lengths. So it's almost exactly like the first set of problems here. So it looks like with these guys being a 45, 45, 90, this side being x, the vertical side's got to be x, hypotenuse has got to be x rad 2. 30, 60, 90, looks like opposite the 30 is y, opposite the 60 is y rad 3, and opposite the hypotenuse would be 2y. Looks like we're dealing with a Pythagorean triple here, so this looks like it'll be 5x, right? 3, 4, 5, scale factor is x. And then, again, 5, 12, 13, which means 13x here. Just multiply each side by x, no worries. Opposite, now this one here is a little weird. Opposite the 90 is x, which means opposite the 30 should be half of that, and then half of that times rad 3. Again, just not really terribly hard. You just have to kind of know the pattern. Let's see here. Let's see if there's any more problems that we need to do. I'll be right back. Turns out I did the problem's a little bit out of order. I skipped 6-14 on accident. So why don't we go ahead and go back and do that one. And I'll go ahead and scroll that down here. So, with your team, determine the missing lengths for each triangle below and try to use your knowledge of these special right triangles and such. So from here, if 13 is going to be my opposite of my 90-degree angle, it's my hypotenuse. Opposite the 30 is going to be 13 over 2, and then 13 over 2 times the square root of 3. Again, nothing, I have to just keep reinforcing. There's not a whole lot of math going on right here. I'm just recognizing the pattern of the 30, 60, 90 right triangle. 18 and 24. Let's see what happens if I divide both of those by 6 and see what happens. If I go and just write a similar triangle here, I'll even just do it in a different color because I want to make sure that it's visible. Let's go ahead and do something like that. 18, if I divide that by 6, I get a 3. 24 divided by 6, I'm going to get a 4, and which means this is a variant of the 3, 4, 5 right triangle. It looks like I'm multiplying everything by 6, so it looks like that's going to be 30 as my third side right there. Sometimes it's good to just kind of reduce that triangle down to its most simplest form here. This side's 25 because we're dealing with a 45, 45, 90 right triangle. Opposite the 30 is 7. Opposite the 60 is going to be 7 rad 3. And then 14 is going to be the hypotenuse. 20 and 52. Let's see what that scales down towards. I have a sneaking suspicion I know what it's going to be. I'm pretty sure if I divide everything by 4, I'm going to get, looks like a 5 and then a 13 right here because 13 times 4 is 52, which means that final side there, is going to be 12. And as long as I re-multiply it by a 4 to get back to the original triangle, I should end up with 48. And then this is 6, which means this is going to be a little weird here because to go from a leg to a hypotenuse, I multiply by rad 2. And let's go and write this down here. If I was to go from a leg to a hypotenuse, So x, and x rad 2 for my 45, 45, 90 right triangle. This is really x times rad 2, right? So which means if I'm going to move from hypotenuse back to leg, that means I have to divide by rad 2. So what I'm going to get is I'm going to get 6 over rad 2 and 6 over rad 2 here. Now in a later section, we're going to learn about how radicals on the bottom are not good. It's not considered simplified all the way yet. So what I'm going to do is I'm going to go through and I'm going to do a process called rationalizing the denominator. And so what I'm going to do is I'm going to get rid of the square root on bottom. The way I'm going to do that is I'm going to multiply the top and bottom by rad 2. Why am I allowed to do this? Well, because rad 2 divided by rad 2 is actually 1, and when I multiply anything by 1, I am not changing anything about it. So what I'm going to do is I'm going to multiply those guys together and get, 6 rad 2, and then rad 2 times rad 2 is rad 4, but that's going to end up becoming 2 anyway, so 6 rad 2 over 2. And because the 6 and 2 are both even, they can kind of cross each other out, and I get 3 rad 2 as the side lengths of each of those sides, so 3 rad 2. And again, same value as 6 over rad 2, but now simplified because we now have a radical in the numerator instead of the denominator. So I think that will go ahead and wrap up this lesson. As always, please leave comments or questions in the comments area, and I will see you all in the next episode.